This is lecture 10 for chapter 5 of Calculus 3, and these are the theorems of vector calculus. In fact, this is what we've done all of Calculus 3 for. Back in the dark ages, like 1.5 million years ago when I took this course, it was only the theorems of vector calculus. You know, proof theorem, corollary proof theorem, that's all we did. We didn't do all the other stuff. In fact, there was always a debate at several places, several universities, as to who taught all the vector stuff. Physics assumed it was learned in math, and math assumed they learned it in physics. So it wasn't even taught. We just picked it up on our own, I guess. So we concentrated on these theorems of vector calculus, and that's what we're finally getting to in chapter 5 now. These are very important theorems. You will encounter them again in electromagnetics and many other areas of physics and engineering, and also in other areas of math. As far as electromagnetics go, these vector theorems are actually give the basic laws in magnetism, electricity and magnetism. You could say they're applications of it, or you could say those laws are implications of these theorems, just depending on which way you want to look at it. So these theorems are going to give some results for the use of the del operator. Remember, you see the del operator as a gradient when it's applied to a scalar field. When it's applied to the vector field, by using the dot product, you get the divergence. By using the cross product, you get the curl. We'll start with the gradient theorem. And we've already talked about this. It now has a name, and it's called the gradient theorem. It says the line integral of a conservative field depends only on the endpoints. Recall that a conservative field is one that is equal to the gradient of a potential field, potential scalar field. And that's what we're saying right here. You might have found out that it was conservative because of the component test, looking at the partials of the components of the vector field f. But after that, you still have to find some function, the scalar function f. Okay. So once you know that, you do need the scalar function to evaluate this. But what this says is that the line integral is independent of path. It doesn't matter how you get there, only counts. The only thing that counts, well, is if somebody did this right, it might count a little bit better. And I could stop and correct all these, but it would just be kind of boring too. Okay, this is f of b minus f of a, right? Because b is the upper integral. Yeah. Okay, so when I've been integrating this vector field along a path going from some point, say a to b, the value of this only depends on the difference in the potential field with that at b minus that one at a. And it doesn't matter about the path, it only matters about the difference in the potential. We see this in electricity and magnetism. You move that charged particle around from one equal potential line of some voltage to another one. It doesn't matter the path, it only matters where it ends up. Same thing holds for the gravitational field, which is also conservative. And of course, if the endpoints are the same, then that line integral is 0. The statement of the gradient theorem involves if and only if. So this means that if the vector field is conservative, then this line integral is independent of path. On the other hand, if the line integral is independent of path, then the field is conservative. So it works both ways. It's an if and only if statement. So that's your gradient theorem, which you know already. And here are two examples which aren't showing up very much. And here you have two locations for this mass, and if you just move it straight up from here to here, that's equivalent from going all the way around here and ending up at the same place. All that counts is the difference between these 2 points. Okay, and this is the electric field, whatever these are. Okay, this is probably like 5 volts, and this is, say, 3 volts. If you start with your particle here and you move from this equal potential point up 5 volts, and you move along this path up to 3 volts, that's the same as if you start here and you move in this path. It'd be also the same as if you started here and moved in this path. All that counts is the beginning and the ending points. And that is the gradient theorem. The next 4 theorems apply both to conservative and fields that are not conservative. And here are their names. Green's theorem, and there's 2 forms of Green's theorem, Gauss's theorem and Stokes theorem. Okay, these are the names of the theorems. Okay, remember Green's is going to have two forms. Gauss and Stokes only have 1 form. I'll talk a little bit about the name Stokes in a minute. What these do is Green, Gauss's, and Stokes theorems, they connect flux and circulation calculations over closed paths and surfaces. And they connect the calculation of the line and surface integrals to the derivatives, certain derivatives on the inside of the region. Green's theorem is for flat regions, 2-dimensional flat regions, and it has 2 forms, the divergence form and the curl form. Gauss and Stokes apply to 3-dimensional regions. Gauss's theorem is the 3-dimensional version of the divergence form of Green's theorem, and it has its own name called the divergence theorem, but it really means Gauss's theorem, and it's 3D. Stokes theorem is a 3-dimensional version of the curl form of Green's theorem. And there's a chart that I'll show you in a minute that kind of matches these up that are probably better than just saying these words. Stokes theorem is also called Kelvin-Stokes or curl theorem because there's another theorem called the Generalized Stokes theorem, and from the Generalized Stokes theorem all of these can be derived. So let's look at that chart. Okay, this is the chart, and in the homework I ask you to reproduce this chart and put in some of the equations because I think this chart summarizes all of it. So Generalized Stokes theorem just sits up here. We aren't going to cover it in this class, but from the Generalized Stokes theorem you can derive all these. Now if you have a conservative vector field, the gradient theorem applies. Okay, see that's sort of in its own column out here. Okay, now let's look at the second column. The second column is going to be used to calculate flux. If you're in 2D, the divergence form of Green's theorem applies in the plane in 2D. In 3 space, it's Gauss's theorem. Gauss's theorem is just a 3-dimensional version of Green's theorem. Okay, in this third column, we're going to look at circulation, and that's a little too dark for anybody to see, so let me find a better, how about this one? Okay, so that works really well. Okay, we're going to use it to calculate circulation. In the 2D plane, there's the curl form of Green's theorem. When you move to 3 space, it's called Stokes theorem. Alright, I'm going to say this once more so you really get it in your head. There's something called the Generalized Stokes theorem from which you can derive all these theorems. If you have a conservative vector field, the gradient theorem applies. For vector fields in general, there are 2 calculations, and we spent the whole chapter kind of doing this. One is the flux calculation, which is integrating the normal component over a line or a surface, some kind of boundary. You're calculating that normal component, so you're getting flux. There's 2 theorems that apply here. Divergence form of Green's theorem in the plane in 2 dimensions. In 3 space, it's called Gauss's theorem. When you're looking at circulation, this is calculating the tangential component of the vector field along the boundary. Boundary can be in a line in 2 dimensions, so then we're talking about the curl form of Green's theorem. When we move to 3 space, then we're talking about Stokes theorem. So kind of have this worked up in your mind, then you don't, I'd look at this first before I read the book, because once you see this, you know where they're going. They try to derive it and have you arrive at this conclusion, which is fine. It's a very nice way to do things. But here's the map. Okay. Now instead of deriving and proving and deriving and proving, which you can do in the book and I ask you to do once in the homework, I'm going to explain them. I will call this the pedestrian explanation of Gauss's theorem, and also it's going to apply to the divergence form of Green's theorem. You can look back on the chart to see that Gauss and the divergence form of Green's theorem are linked. You haven't even seen these theorems, but that's okay. Let me explain it to you. Let us say that you are sitting in a house and you have a certain amount of money. You have stuff in a drawer, you have stuff in the freezer, you got stuff in the mattress, whatever. You've got a bunch of cash in your house. Right. So let me draw a semblance of your house. So this is your house here, and you're sitting in here with this money. I guess money's green, so we will, or usually it's green, so we'll put some green money in your house like this. Now, here along your house you have various, there's various windows, you've got a floor, and let's say various people show up and they give you some money. Maybe they pay you back, or maybe this guy fixed your floor and he wants you to pay him. So right here you have money coming in. I should have done this perpendicularly. You have money going out, straight out the floor. Some guy fixes your roof. You got money going out here. Somebody shows up to pay you, repay your loan. It's coming back in. So you see all these vectors going in and out. Of course, cash is a scalar, but you kind of get the idea of what I'm talking about here. The movement of cash. All right. So now the question is going to be, at the end of the day, what is your change in your fortune? There's two ways you could do this. So let me go to the next slide because I have the words on that one. But you see the idea. You've got these bill collectors and all these people coming in. You've got money going out, and sometimes you have money coming in. So the edges of the house are the boundary, and they are totally enclosing, their closed boundary, enclosing the region inside, the enclosed volume, which is, I guess, your living space, or rather the hiding space for your money, however you want to look at that. Now this is going to be the question. What is a change in your fortune by the end of the day? At the end of the day, let's say. There's going to be two ways to figure this out. One way is the flux way. You could add up all the money that came into the house and left the house. That would give you the change. You have to pay out $10,000 in bills and people show up to give you $5,000 repaying your loans. Your change in your fortune is going to be the difference between those two amounts. You're looking at the flux, the amount going in and the amount going out, and you're adding those up. That's the flux way. Now, the divergence way is you have, say, the sum of money that's in your house at the beginning of the day. You add up all the stuff at the end of the day and you subtract them. That's the divergence method. So the flux method occurs at the boundaries. So the flux has to do with the boundary, and the divergence has to do, I'm going to write it, with the region. Okay, you see those two ways, and they would be equivalent. Now if you understand this, which is pretty pedestrian to say the least, then you have an understanding of these theorems. Like I said before, the difference between Gauss's theorem and the divergence form of Green's theorem, the difference is the dimension of the regions to which they apply. Gauss's theorem applies to three-dimensional volumes like the house. Okay, so the region is 3D and the boundary is 2D, surrounding surfaces. For Green's theorem, it applies to a flat two-dimensional surface. So in this case, the region would be a flat surface and the boundary would be a curve going around it. In the written text, I was thinking you might have an example of, say, a stockbroker standing on a floor, and the region, it would have to somehow include his telephone, but forget that for a minute. The region would be the floor space around him, and then any exchanges that went back and forth around that outside of that floor space would be the flux. What happens inside is the divergence. And now, here is the statement of these theorems. Let's look at Green's theorem. For a flat region bounded by a simple closed surface with positive orientation, We're going to let n be the outward normal. The integral of f dot n over that surface area, again, you're going to have to add the parameterizations into it, but you can see f dot n is going to get you the normal component of the flux across that surface. N is the outer normal. So if money, in this case, before was leaving, then that would be positive. If it's coming in, it's negative. That's okay. All right. This is your flux calculation on here, and that's what we've done quite a bit of in the last couple of lectures. That's your flux. That's equivalent to integrating the divergence of F over the enclosed area. Here it is in 3 dimension. I have some I use some notations here. I try to be kind of standard of it. ds and delta s those were 1D curves. Okay, sigma is a surface. All right. Now in 3D, the enclosed area is a volume. That's why you see dV here. But this is the divergence. Remember what divergence is? You know what the del operator is. d by dx in the I direction. Okay, plus d by dy in the j direction, d by dz in the k direction, and we dot that m in the I direction, n in the j direction, and plus p in the k direction, and then we take the dot product and take those derivatives. So we'll have, again, a scalar, right, because it's a dot product, the derivative of m with respect to x plus the derivative of n with respect to y plus the derivative of p with respect to z. We find that derivative and we integrate that over the volume, and that's equivalent to taking the function, dotting it with the normal, and integrating over the surface. There are many other things you can do besides just calculate flux with these theorems, but they're used very often to compute just the flux, and the integrals I put in a box are usually much easier than the ones on the other side. Now the other theorem to explain is Stokes Theorem and the curl form of Green's theorem. Those are going to have to do with the tangential component of the boundary. I call this diagram a kiloword. Okay. If you looked at all the little eddy currents that are going around in some area, say this area, this area, this area, and this area, and you want to add up all of this swirling, obviously, let me get rid of those for a minute. Okay, obviously, these are going to cancel. Where the little eddies kind of run into each other on the side, they cancel. And all that's left is the outside edge. So, in other words, this would be the curl throughout the region, and this is, I'm sorry, curl doesn't have an E on the end, so this is a curl, yeah, that's right, of F over that region. Okay, that's that integral there, knowing that these are going to cancel, but you don't worry about it because actually it's an easier calculation, but it is equivalent to this, which would be the integral of f dot t over the surface, s or d sigma, depending on the nature. So that's what we're talking about with these curl forms. We're talking about the curl form of Green's theorem and Stokes theorem. There are a few more words in the written lecture, but I'm going to move right now to the statement of these. Okay, because now I think you have an intuitive idea of what's going on. So the curl form of Green's theorem. Remember, Green is going to apply to your xy plane, to your flat regions in space. It has to be bounded by a simple closed curve. Okay. Previously, we studied how to do this integral over the boundary. Over the boundaries, like say, of a surface, and where we're looking for the tangential component all the way around, looking for the circulation. Correct? Okay, we did that in other lectures, and this is what we did right here. The little zero that you can't read down there means it's a closed surface. Okay. Alright, so you look all the way around and you take f and you dot this vector function with the tangent in order to find the tangential component of it, and then you essentially add it all up as you go around the surface. Okay. in Green's theorem, that is equivalent to taking the curl of f, then you have to dot it with k being normal to the plane, and integrating over the inside area. Stokes theorem is for curved surfaces and in 3 space, okay, in the 3-dimensional space, and here you go again. You can take, you see it's a little, it's not quite the nice analogy you have for Green and Gauss because of what it applies to. There are certain things these theorems do not apply. Okay, so again you have to take f dot d times ds, and that's your boundary over that surface. Or you can look at the this is a surface like this, and it has a boundary around it. Is what we're talking about. Or you can take the curl dotted with a normal to the boundary, and integrate over the surface area of it, and that's equivalent.